Hi, welcome to the part 1 of the series where we'll be creating a BookFinder application, an application to find books. The tech stack is Spring Boot and Elasticsearch, and we'll also be using embeddings generated by OpenAI. So if you want to follow along, you should have OpenAI account and OpenAI API key. The dataset we'll use is Kaggle 7K books dataset by Dylan J. Castillo. Let me show you this dataset. So we can see that the license is public domain, and you can click download to download a books.csv file. Here we can see the structure of the data we will be getting, and we've got ISBN numbers, which are like primary keys in the book world. We've got the title, subtitle, authors, categories, thumbnail URL, and also description of the book, published year, and average rating. How are we going to search for these books? First, we'll do the full text search, which is search by keywords. And that's why I have chosen Elasticsearch, because Elasticsearch is primarily a full text search engine. But Elastic can also do semantic search, which is search by meaning. When we've got full text search and semantic search, we'll combine it into a hybrid search. And hybrid search merges the results from both of those searches into a final ranking. In this video, I will tell you what exactly is full text search, semantic search, and hybrid search. I will show you the architecture of what we will be building and some example corporate architecture. There will be no coding in this video, so if you want to skip to the next video, it should be in the description. Full text search finds documents by matching the actual words from your query against the words in the documents. So, for example, you may be searching for a dystopian world, and you may find something like this. All armies of the world, including the Tribulation Force, head for the Middle East to engage in one massive battle, as the world becomes even more dangerous to live in, with death, mistrust, and treachery all around. It just found a document where the word world is occurring twice. It's not really a dystopian book, I think. The Elasticsearch is using BM25 algorithm, and BM25 is a ranking algorithm. So it scores how well a document matches the search query. And on the high level, BM25 takes into account things like term frequency, inverse document frequency, and long documents are penalized. So term frequency, how many times the world and the dystopian occur in the document. Inverse document frequency means that the rarer words count more. And long documents are penalized because if you've got more words in the document, it is more likely to contain the searched term. Semantic search finds documents by meaning rather than exact word matches. By using the same search term, dystopian world, we will find book with a description like this. In AD 2600, the human race is finally beginning to realize its full potential. Hundreds of colonized planets scattered across the galaxy host a multitude of prosperous and wildly diverse cultures. Genetic engineering has pushed evolution far beyond nature's boundaries, defeating disease and producing extraordinary spaceborne creatures. We do not have the word dystopian or the word world anywhere in this description, but the description itself matches the search term dystopian world better than the previous one. On the BookFinder startup, we'll be vectorizing the 7,000 books from the CSV file. We'll be vectorizing book titles, subtitles, and descriptions. We'll use the text embedding free small embedding model by OpenAI. And after we have the vectors, we'll save them in the Elasticsearch database. The vector is simply an array of values, and it represents meaning of the vectorized text. Why do we even need some vector? Well, text embedding free small produces a 1536 dimensional vector, but the intuition is the same as if we were working with a two-dimensional vector, so let's start with it. On the application startup, we have vectorized book descriptions. So in a two-dimensional space, a vectorized book description could be represented by this vector. We will also be vectorizing the search query, so the dystopian world. And if these two vectors are close to each other, are similar to each other, then it means that we have a match, because as I have said earlier, a vector represents meaning of the vectorized text. So we've got a user query dystopian world, vector with 1536 dimensions. We've got the book title, book description, and book subtitle vectorized, and we get another vector from it. And now the only problem we have is how to check how similar the vectors are. And to tell it, we just use cosine similarity. We don't really have to calculate it. The library will do everything for us. Semantic search flow. We'll get user query, dystopian world. Then we will get the query embedding from OpenAI. And with the obtained embedding, we'll be able to search semantically in the Elasticsearch. Hybrid search. In hybrid search, we do full text search and semantic search at the same time. Both of these searches will produce a ranking of the books, and we will merge the two rankings into the final ranking using the RFF algorithm, which stands for Reciprocal Rank Fusion. I will explain you more about Reciprocal Rank Fusion, but first let me show you an example for the search query dystopian world. So for example, the top result for the hybrid search is how to build a time machine. For the full text search, it was the 5th best match, and for the semantic search, it was the 31st best match. The second one is Brave New World and Brave New World Revisited. For the full text search, it was the 8th best match, and for the semantic search, it was the 27th best match. RRF looks only at the documents positioned in each list. Here you've got a formula how to calculate it, but it's much easier to show it in practice. So the first position in our ranking is how to build a time machine, and it was 31st in the semantic search and 5th in the full text search. To calculate the RRF score, we take 1 over some constant, which is usually 60, plus the position in the first list, plus 1 over constant, plus the position in the second list. And we get the score, which is 0.026374. calculations for the Brave New World and Brave New World Revisited. 1/60, position in the first list, 1/60 plus position in the second list, and we get 0.026200, which is less than the score for the how to build a time machine. Why is the K60 usually? Well, it works well in practice, and if it was 0 or 1, or if it was much lower than 60, the difference between first and second place on the list would be quite huge. To sum up the architecture and setup, we'll have a Spring Boot application, and inside the repository we'll have books.csv file. On the startup, if there are no books in our Elasticsearch database, we'll save the books, then we will call the OpenAI API to get the embeddings, and finally we'll update the books with the embeddings in the Elasticsearch database. The same Spring Boot application will have endpoints for full text search, semantic search, and hybrid search. Our app architecture is very simple, which is fine for learning purposes, but in a corporate environment you can expect a much more complicated setup. So let's talk about it for a moment. Let's assume that we are talking about e-commerce website selling books. First of all, we'll need a mechanism to create books in the system because, well, we won't have books.csv file. We will have a book service which will get a request to create book, and the book will be saved in a relational database. The relational database will be our source of truth because as an e-commerce website, we've got some other relations, some other data in our database, and we need relations. But anyway, we will need the book in the Elasticsearch database because we want the books to be searchable. So we need to bring the data somehow to Elasticsearch. Usually it is done with Kafka. So the book service will publish the book created event to a Kafka topic. Actually, here I have a oversimplification because there is a problem with this setup. The book service can break after saving the book in the relational database, and then the publish book created event wouldn't take place, and the book wouldn't be synced to the Elasticsearch database. And that's why in production, events are written to an outbox table first. The outbox table is an additional table in the relational database. And then a separate process publishes the book created event to Kafka, preventing event loss. Next, we have the indexer service, which is consuming the messages from our Kafka topic. So it gets the book created event, generate embeddings for the book, and saves the book together with the embedding in the Elasticsearch database. Here you can see that it says eventual consistency, which means that Elasticsearch will eventually have the same data which is stored in the relational database. Right now, we have our data in Elasticsearch. So the final thing which we need is the search service. So a search service will be a separate microservice which will get a search request, embed the search query, and do a hybrid search and return a response. That would be all for now. See you in the next video.